Okay, welcome to this talk about efficient verification of Boson sampling. This is a paper which we put on the archive a few months back, and it's a joint work with Frédéric Grosshans, Elham, Kashefi, and Damian Markham from Sorbonne University. And this is a part of this work was done when I was doing my PhD there in Sorbonne University, and now I'm a postdoctoral scholar at California Institute of Technology. So the motivation for this work is quantum speedup. So this idea that a quantum computer can perform efficiently a task which is intractable for classical computers. And the famous example of this, which sparked a lot of interest into the field of quantum computing, is the celebrated Shor's factoring algorithm, because it is believed that it's hard to factor integers efficiently with classical computers. And this is actually what a lot of cryptographic systems are based on, this believed hardness of factoring. And so we anticipated that quantum computers could solve not only this problem, but maybe more interesting problems. But the road towards this, quantum speedup over classical computers is long and tedious. The quantum circuit to perform factorization of large integers is still far from reach. And so instead, like a big milestone of the field is this demonstration of quantum speedup, the kind of specific purpose machine that are engineered especially for this task, for the task of demonstrating quantum speedup, of beating classical computing. And there are a few requirements for this quantum speedup demonstration. So one thing that you need is a hard problem, just like factoring, for a problem which is hard for classical computers. A device that actually solves that hard problem, and that is simple enough that we can hope to build in the current state-of-the-art experimental components. So, for example, you have models like Boson sampling, IQP circuits, random circuit sampling. All these models that are kind of designed in this purpose of providing quantum devices that are hard to simulate classically, but still, can be implemented in the short term. And last but not least, you'd want a verification that a quantum device solved the hard problem at hand. So to kind of summarize, you have this problem that you care about, just like factoring. It's hard to solve for a classical computer, and you want to build a machine that solves this problem, and for which you can prove I solved this problem, so I demonstrated quantum speedup. So where we're now is that there have been few actors now in the field that have claimed this quantum speedup demonstration. So the first was Google in a Nature paper in 2019, where the hard problem was something inherently quantum, the fact of sampling from a random quantum circuit. The simple in quote quantum device was this nicely pictured here 53-qubit processor Sycamore. And the verification that was performed in this work was, in some sense, a validation of the experiment, which was based on a noise model and some specific cross entropy benchmark. Then there was the USTC photonic experiment, where the hard problem was instead Gaussian boson sampling. So the problem of sampling from the output probability distribution in photon number of some complicated optical state. The simple quantum device here was a 100 mode interferometer that you can see on the right. And the way verification was performed is again some like validation based on incomplete benchmark. So you see that in both of these cases, you have a hard problem which is well identified, a quantum device which at least claims to solve the hard problem, but the verification is in some sense incomplete, and I'll expand on this in the upcoming minutes. So ideally, what you would want of a verification of quantum speedup is that you can envision the experiment as some black box, right, which outputs some classical data. And your task is to make sure that this classical data actually correspond to the, actually solves the problem. So here correspond to the output of some specific probability distribution. So the problem is exactly the nature of the task at hand. So all these sub-universal quantum speedup proposals, Boson sampling, IQP random circuit sampling, are sampling problems like their names indicate, meaning that the computational task at end is really something where you want to output random samples from some probability distribution. So what the actual output that you'd see of the device would be a bunch of random numbers. And so verifying this, that the quantum device has achieved the computational task, has performed the computational task, is asking, like check that these samples are from the right probability distribution. And this is something which is well known to be extremely hard to do in this case. For these specific type of probability distributions, it was shown recently that there's no hope of an efficient, direct classical verification. The reason for this is that you get all these bunch of random numbers, and one property that makes the computational task hard is that the probability distribution from which they are supposed to originate are anti-concentrated, and so they are not like too peaked. And so it's kind of hard to efficiently verify, like all the probabilities are exponentially small. And so it's hard to just given a polynomial number of samples, it's actually impossible just directly to use them to say, okay, they're from the right probability distribution. And so instead, we can still try to do it, right? And we can still try to verify by making additional assumptions. So like a common thing that you do is I have some experiment, I maybe know how it's working. So I assume, some noise model, or instead what I could do is I expect, to be sampling from some ideal probability distribution. So what I can do is instead of verifying that I'm actually sampling from this specific probability distribution, I can verify that the probability distribution from which I'm sampling has common features with the one I should be sampling from. So these are more like confirmation or validation of the experiment. Okay, so the thing is, it's very hard to do a direct verification of these experiments, but at least we can try. And one step in this direction is to say, okay, let me try to make the least assumption possible on the device at hand. So this could be some, computational assumption, some conjecture you make about a problem being hard, or giving some minimal, computational capabilities to the verifier. So in this picture, you can think of this black box as being the experiment, the quantum speedup experiment, and the part on the right here as being the verifier or the experimentalist that wants to, certify the output of this experiment. And so the direction we took in this work was to say, well, if we cannot do an efficient, direct, classical verification, maybe we can still do something which is efficient by providing the verifier with minimal quantum capabilities. So in this case, assuming that the verifier has simple measurements, with the hope that this would make the problem simpler and the verification possible. So this would be the picture. You have some experiments, you ask it many times the same output, and then you make a bunch of measurements on these outputs. You get the measurement results, you do some post-processing, and you'd like to come to a definite answer. Is this state close to the ideal state that you should be supposed to prepare? And what if I now measure it with the right detection? Am I doing something which is classically hard? Okay, so we can expect that this is a bit easier because we're giving the verifier some very minimal computational power. But this is exactly the setting of quantum tomography. Like you're given a state, you make some bunch of measurements on many copies of it, and you're asked to make a statement about what the state is, some properties it has, something like this. And the cost in terms of number of samples that you need say interesting things about the state actually scales exponentially in the size of the system at hand. So if we were just kind of brute forcing, making measurement and trying to make predictions about the state, then this just wouldn't be efficient. And actually the, outputs of these sub-universal model, they're super entangled. They're really kind of populating the Hilbert space. So there's no like a simple shortcut that you can take that avoids this exponential curse of tomography. So is this really simpler? And so in our work, what we show is that, yes, in the case at least of boson sampling, of the original boson sampling with single photon inputs, this is possible. One can achieve an efficient verification of the output states of any boson sampling experiment using simple Gaussian measurements. So I'll expand a bit on this as well, if you don't know what this is. But the main point is that we only ask the verifier to be able to do these single system measurements. Okay, and the specific type of measurement that we're considering is the so-called heterodyne measurement, which is something which can be achieved like with state-of-the-art detectors with very good efficiencies. So maybe before explaining what these measurements are, let me recall what boson sampling is, because I've been keeping mentioning it. So boson sampling is this model of computation which was introduced in 2010 by Aronson and Arkhipov. Where you have a bunch of, so here these ones and zeros represent photon number states. You can think of this as, so this is for any bosonic system, but in general, you can think of this as in the optical setting, these guys being single photons, one in each spatial mode, and this is just vacuum state. And it enters some interferometer. So this is essentially just a kind of a computation made of beam splitters, phase shifters, reflections, and essentially some optical path. And at the output here, one measures the photon number at each spatial mode. And one property of these interferometers is that they are passive. That is, the number of photons you put in gives you the same number of photons you put out. So here, for example, you have one photon in the first n modes for a total size of m modes. And here in the output, maybe you'll detect photons elsewhere than in the first n modes. But in the lossless case, you should detect n photons. And what they showed is that this computational problem, the problem of sampling from the output photon number probability distribution of such a device, is hard for classical computers and under some like reasonable complexity theoretic assumptions. And maybe an intuition behind this is that, this is the expression given just by Born rule of the output probability distribution for some sample S. So here, S1 would be the number of photons detected in the first mode and so on up to Sm. And you collect them into a vector, you get a probability distribution for each possible vector. And that's just the quantum expression for the value of the associated probability for each outcome. And it turns out that this is related to a combinatorial quantity, which is called the permanence of a matrix describing this interferometer, which is hard to compute. And so you can kind of link this to the hardness of sampling. But the main contribution of Aronson and Arkhipov was to show that under additional reasonable conjectures, the same model was actually hard to sample for classical computer, even approximately. What that means is that now the computational problem at hand is not sampling from this ideal PS probability distribution here, but instead from any noisy probability distribution, which only approximates that ideal probability distribution up to some total, like constant total variation distance. And this is very important because now if you think of trying to prove this experimentally, the fact that you're achieving something quantumly that is hard to do with classical computer. Well, even if you do your best building your best boson sampling device, in the end there will always be noise, errors, and the best you can hope to achieve even quantumly is sampling from a not ideal, maybe near to ideal noisy probability distribution. So it's actually very important for any experimental demonstration that we have this theoretical statement that even sampling from approximate version, a noisy version, would still be hard. And so this was shown as well in this paper. Okay, now you can ask, how do I verify something like this? So just to give you an idea, here you start with a tensor product structured state. It enters into this interferometer, and in the output, you get something like super entangled in terms of photon number between all these modes. And this is the task at hand. We have in the ideal case, we would have a Boson sampler like this. It would generate some output state here, which I call here a psi BS, some pure state. And that would be, this box would be your experiment. It would generate some M mode, maybe mixed state row, and you want to compare these two objects. The reason is because if you achieve that feat, if you're able to certify here, for example, that the fidelity between the state you produced and the output state of the Boson sampler is big enough, close enough to 1, then it actually implies that the output probability distribution of whatever measurement you do on that M mode state that you produced would be close in this same total variation distance to the probability distribution that you would get by measuring that ideal state with the same measurement. So what this means is that if we have a way of certifying this, of providing lower bounds onto the fidelity between a state produced by a Boson sampling experiment and the ideal output state of a Boson sampler, then we're able to check if we achieve that condition, right? And this total variation distance closeness, and this is exactly a condition that enables us to claim this quantum speedup. Okay, so this is our goal now. I'm going to explain how we managed to obtain an efficient protocol for doing this. Maybe the first notion, which is interesting, is that in general, in kind of the certification field, you'd heard about fidelity estimates. That is something that tells you how far you are from some given target state psi. Here, we only care about fidelity witnessing, that is obtaining a lower bound on the fidelity. And so here is kind of a depiction of what you do. Instead, you only care about how close I am to the state, but you don't control like the interval. You just care, I just want to be close enough to that state, because then I can claim that my probability distribution is close enough to the ideal one. Okay, and so what we do is we actually obtain just lower bounds, like tight lower bounds on the fidelity. So if you have your state, experimental state rho, and this ideal state psi, what you obtain, you just run a protocol, which I'll describe in a second. And the verification protocol is going to estimate a witness of the fidelity, so a tight lower bound on the fidelity, which satisfies this equation. So you can think you have this protocol, and it gives you this value W, and this is F, this fidelity you want to lower bound here. And so this is the kind of tightness that I was talking about. You see that when the fidelity is very close to 1, then the left-hand side here will also be close to 1, and then the witness is also close to 1. So when in the regime that you're interested in, where the fidelity is very close to 1, you can essentially replace the information about the fidelity by the information about this witness. And this would be especially interesting because the witness W is obtained efficiently, whereas we don't know of a way of actually gaining the information otherwise efficiently on the fidelity. And for constant precision in the estimate that you get and constant success probability over the samples that you obtained, this is the number of samples that you need. So M again here is the number of modes. So you see it's efficient in a sense, it scales as M squared log M, and it would just means you have your experiment and you press the button giving you an output state this big N times. You make all the measurements, and then you do the right post-processing to obtain the value of the witness. Okay, so this is the detection that has to be performed. So briefly, these two circles here represent like sub modules in that detection, which are called homodyne detection. This is a very common detection type in the optical setting. And what this detection does is just it does it like a double homodyne detections. The details are not too important. But what's important is that it's a fixed measurement setup. Like in general, for people that are aware about that know homodyne detection in general, you have some phase that you want to vary to measure a different observable. In this case, you just have a fixed measurement setup, and you always do the same measurement. And here, these dashed red lines, they represent beam splitters. So essentially what happens here is that you have your input unknown state that enters here. It's divided into these two branches. You mix it with some vacuum state on a beam splitter. And then you're going to essentially do homodyne detection of the two branches. And yeah, that will give you some sort of noisy joint detection of quadrators of that input state. Okay, and there are different versions of this detection. Either you can have a balanced detection when this beam splitter is 50-50, splitting the detection of the two quadratures evenly for the input state, or you can also unbalance it. And this very, like at a very high level, this corresponds to playing with the uncertainty principle. So these kind of Q and P that you're measuring on both sides, these are conjugate operators. And essentially when you unbalance the detection here, you decrease the uncertainty for one observable while increasing the other ones, respecting the uncertainty principle. Okay. So this is what the protocol would look like. I already described it previously. You have your experiment, you press the button n times, so you get n copies of your m mode state. And then on each of these modes, the verifier or the experimentalist would have to just measure heterodyne detection for all the modes and gaining an output. I should have said that these detections here, homodyne detection, both of these detection yield a real outcome. So here Q is some real number, P is some real number, and we form the complex number alpha equals Q plus IP. So you can think of this detection as really like mapping some quantum state to some complex number, and you just samples these alpha from some probability density, which depends on the input state. Okay, and so what the protocol does is that you collect all these numbers like alpha 1, alpha m1 up to alpha 1n, alpha mn, and you do a big classical post-processing. You shake everything. And in the end, you can kind of invert this thing to obtain an estimate of the fidelity witness W that I was mentioning before. Now, this estimate yields to a tight lower bound on the fidelity. This lower bound on the fidelity itself gives you a bound on the total variation distance, and putting everything together. So everything is tight in the regime where the state is close to ideal, and putting everything together, this is sufficient to do the verification. So how does this classical post-processing step works? Because like all the complexity of the protocol is hidden in that box essentially. So there are two things. One is that this classical post-processing, so it gives you this multi-mode fidelity witness. And the way it does it is that it's going to estimate single mode fidelity witnesses and turn them into multi-mode fidelity witnesses. So the trick essentially, I was mentioning that the output state that you would get in general and that you would target, the ideal one would be in general, very entangled and very hard to parse. So the idea is that actually there's a specific property of the detection that you may use. So I was saying this, so this kind of schematic here represents this heterodyne detection that gives you a complex outcome alpha. And we're going to use a trick here that lets us, or rather lets the verifier undo some quantum operation by an action on the classical data. So at the high level, this is the idea. What the verifier could do to verify the Boson sampling state, which is a bunch of single photons, vacuum, and then that big U operation acting on that input. What the verifier could do is undo the U, apply a U dagger, and then make their detection, because then the state to verify is much simpler, right? It's only this tensor product of ones and zeros. But now, if you ask this from the verifier, well, you have a protocol which is much more complicated, right? Then the verifier is almost able, like up to this generation of single photons, the verifier is almost able to do a Boson sampler themselves. So the trick we use is the fact that actually there's another way of implementing exactly this, like this reversing unitary U dagger and this tensor product of heterodyne detection. You can do like this. Instead, you can like measure everything, with heterodyne detection. So you would get complex numbers, gamma 1, gamma n, and then apply some classical post-processing directly on the classical samples. And it turns out that if you do the math, you'll see that the map that maps some quantum state, which is measured here, to the classical outcomes there, or similarly that would map some quantum state here to the classical outcome there, is exactly equal in the two cases. So the reason for that is that broadly speaking, this detection projects onto so-called coherent states, okay, that are a family of well-known states in optics. And these states, they evolve very simply through these transformation. They don't get entangled. And so you can essentially reverse the action of this quantum operation just by doing a classical post-processing. And then the other step now that we're there is that we're left with verifying these kind of tensor products of input state, these ones and zeros. And this is actually a straightforward construction that lets you build multi-mode fidelity witnesses for tensor product of pure states just from single mode fidelity estimates. So it turns out these detections at the single mode level, they're tomographically complete. So you can just do fidelity estimation with these detections for each of the modes and turn all the single mode estimates into multi-mode witnesses. Okay, so summarizing the protocol, the verification protocol is Gaussian. What we call Gaussian is like all operation projects or map Gaussian states to Gaussian states. And the Gaussian states, if you don't know what that is, you can think of this as the equivalent of Clifford states or Clifford operations in infinite dimensional Hilbert spaces. And these are the simplest operations to implement experimentally, and also in the theoretical setting, these are also the simplest operations. If you have some Gaussian quantum computation, just like Clifford, you can simulate everything efficiently. So now we can ask, is the whole process Gaussian? So we saw that the verifier has to make these measurements, these Gaussian measurements. They project onto coherent states. These coherent states are Gaussian states. But once the output state of the experiment is certified, well, you still want to perform the hard task, right? Once the state is certified, you want to measure the output state with actual photon number detection, just like in the original Boson sampling, to demonstrate quantum speedup. And this photon number detection projects onto Fock states. These are not Gaussian, so it's not efficient. Oh, sorry, it's not Gaussian. And instead, actually, the verifier could also measure the output state with unbalanced heterodyne detection. Remember that I said that you have these two types of heterodyne detection depending on the balancing of one beam splitter. And there's this construction that actually you can do Boson sampling, but in the output, you can replace the photon number detection by unbalanced heterodyne detection. Okay, and these, what they do is they project onto squeezed coherent states. These are also Gaussian states. So effectively, all this part is Gaussian. You may think of this construction as the time-reversed version of the Gaussian Boson sampling computational model, where instead it's Gaussian states evolving with the Gaussian evolution and measured with some photon number detection. And in this case, it turns out that this is also hard to sample for classical computers, at least in the exact case, like sampling from this ideal probability density. Here we showed a few years ago that it's hard to sample for classical computers. And this is nice because it means that now you can, in a single setup, switch between the quantum speedup demonstration, the hard to sample probability density with unbalanced detection. And then just by changing the reflectivity of the beam splitter, you switch to a setting where you can verify. So this is kind of as minimal as we get in terms of assumption, like you trust only these specific single mode heterodyne measurements and your tuning of beam splitter or something. Okay, so let me conclude there. The result is an efficient protocol for the verification of photonic quantum speedup experiment using these trusted measurements. It uses single mode Gaussian measurements, these heterodyne detections, and there's a way of making it work for the verification and the hard sampling task. Now I briefly talk about the assumptions, but In all the talk, I was considering that the experiment is always outputting the same state, but you can also remove this assumption. So we have another version of the protocol which does not make this so-called IID assumption. And it works for larger class of multimode quantum states. So this trick about coherent states evolving simply through interferometers, you can kind of generalize it and use it not only for demonstrating quantum speedup, but the next gen of photonic quantum speedup computations. And of course, there are open problems still. So the first one is that if you want to do everything in the same setup with these unbalanced heterodyne detection, the sampling harness is only demonstrated for the exact case. I guess there was not enough motivation for proving it the average case approximate sampling harness, but now there is. So that's an interesting open question. And the other one, of course, is that since we're talking about verification of quantum speedup and quantum versus classical, in the ideal case, you would just want a setting where you would get classical outcome, and you would not need to require the verifier to perform any quantum operation at all. You don't want to trust quantum at all. And so is there a way to tune this protocol to make the verifier classical? And so here, kind of the possible ideas would be similar to these protocols of verification of universal quantum computation, where you leverage the power of a prover using classical, like post-quantum cryptography. And so it would be interesting to see if it's possible to make it work still in an efficient manner in this case. And so with these open questions, I'll thank you for your attention.